So we left off talking about the ideal gas law, PV equals nRT, which relates the four fundamental quantities associated with gas to one another. Again, for a given gas sample, these components are not independent of one another. If you change one, you ends up altering the others. So those four quantities, again, are pressure, volume, number of moles, and temperature. And they're all related via this proportionality constant, which we call the gas constant, which for us usually has the unit 0.821 value, 821 liter atmospheres per mole Kelvin, which suggests strongly that the units for volume would have to be in liters, and the units of pressure would have to be in atmospheres, N would be moles, and T would be in Kelvin. Given any three of these, we can calculate the fourth, and as we've seen, it's very easy to measure the pressure, volume, and temperature of a gas. So it's a very convenient way of finding the number of moles. Well, we've already seen numbers of ways to find moles, and so we can now add this one to our arsenal. Given volume and temperature and pressure, we can convert that to number of moles using the gas law. So now we can add that to our other pile, molarity and a volume, and grams and a molecular weight, to convert between two units. And we can also spit these out. Let's not forget Avogadro's number. Alright. So this is one way of dealing with using the ideal gas law. But there's another more subtle way of utilizing. If we actually look at the gas law, PV equals nRT, the definition of what a mole is, well, again, depending on how we look at it, one of the ones we talked about in the last week's lecture was that, well, given a molecular weight and a mass, you can determine the number of moles. But if we actually look at what molecular weight means, that is defined at the molecular weight. It's defined as the grams per mole of a compound. And usually, again, this is 1 mole. It's the grams per 1 mole. 18 grams per 1 mole of water. That's the molecular weight. The implied information in there is that if we know the number of grams of a compound, and we know the number of moles of a compound, the number of grams we can usually get from the balance, and the number of moles we can usually get from other methods, like maybe gas laws, we can combine the two and determine the molecular weight. So given a mass and a number of moles, you can calculate the molecular weight of a compound. And so if we plug that in, we substitute molecular weight into this equation, moles, so the mole is equal to the grams of a compound divided by its molecular weight, effectively. And so we can substitute that into our gas law and obtain the following. We can get the molecular weight, we can rearrange the molecular weight. Equal to grams RT divided by PV. Well, grams per unit volume, that's density. And so we can also use the density of a gas to determine its molecular weight. Implied in this is also that the more dense a gas is, the higher the molecular weight of the gas. And so you can actually use relative buoyancy of balloons to sort of determine the molecular weight. Not an easy experiment, but you can actually do that. But more often than not, you can easily calculate the molecular weight. So you can use this expression to find the molecular weight of a gas given the mass of the gas. Again, it's very easy to measure the volume, the pressure, and temperature of a gas. And we know how to measure mass. So all we have to do is evaporate a compound at a known pressure, volume, and temperature, and from the mass of that material, we can calculate its molecular weight. It's actually something we do in one of the labs. So let's see what this looks like in practice. This is a typical chemistry problem. You look at it, and it doesn't seem like it has enough information to solve it. It doesn't even seem like it. What kind of problem is this? You know? We see that there's some analysis, there's some percentages, and so we see that this is 33% silicon and 67% fluorine by mass. And they say that they want us to determine the molecular formula. Well, we've seen problems like this, but they also throw in this little gas law component. They say that the mass of the material was 2.0 liters, was found to be 2.38 grams at STP. Again, STP stands for standard temperature and pressure, but more likely it means 0 degrees centigrade, 1 atmosphere of pressure. So, how do we go about this? Well, this is really a two-component problem. As is typical with problems, there's often work that needs to be done. In this case, one of the things that they're asking us to do is to find the formula using your standard techniques that you would do for elemental analysis. I'll leave that up to you. So, running through this calculation, we find that an empirical formula of SiF3 was determined. Again, the empirical formula is not the molecular formula. The molecular formula is a whole number multiple of the empirical formula. So the question is, what is that whole number? All right? And so we have to use some other method to determine the molecular weight. Remember all those problems we did when we said, oh, find the real formula is X. This is how they figured it out, one of the ways. So how do you determine the molecular formula of the compound? Well, I guess what we really need to know is, what is the molecular weight? Well, lucky for us, we just spent the past 5 minutes calculating a formula for the molecular weight, which would be the molecular weight of a compound would be equal to the mass of that compound divided by the volume of that compound times the pressure, define gas constant R divided by P. And so we can plug in various quantities from our problem and find these values out. So we're told that it's STP, which is at 273.15 Kelvin, as our temperature. Our pressure was 1 atmosphere, in this case pretty easy. Our volume is listed as 0.210 liters, and our mass was listed as 2.38 grams, leaving us just our gas constant. Let's figure out the number of moles per grams per mole as our units out. Setting this up and calculating, get a molecular weight of 254. Well, if the empirical formula weight, so this would be our molecular weight, the molecular weight divided by the empirical formula weight is equal to the number of empirical formulas present. Hope this works. We get 3. says that there are 3 empirical formulas, and if this one was the empirical formula, this would be equivalent to an Si3F9 compound. So, what we're going to start to see is that often these problems have components from other aspects of chemistry, solutions, stoichiometry, elemental analysis. But the trick with most of these is moles. Even if we didn't go this more complex route where we actually had this formula, you could have done the standard calculation. Mole is equal to PV divided by RT. And then from the number of moles, you take your grams and you divide it by your moles, and that will give you the molecular weight. There are often more than one way to do these problems. One last concept in dealing directly with gas laws is this idea of partial pressure. One of the behaviors of a gas is that gases, when they're mixed, it's as if each gas behaves independently. And so we can calculate the effects of each component as if it was just alone in a container. So we have a container of gas. That has a certain volume, certain pressure of gas, and the gas molecules are zipping around in there. Actually make that sound. Right? And then you have another volume gas, same size container, at a different pressure, and those molecules are also in a different container. We could do the calculation for each of these on their properties, and then if we were to combine the 2 containers, we would see that their properties would be an aggregate of the 2. The only thing that would really change would be the pressure. PA plus PB will equal P total. There's no serious deviation from that. Unlike solutions where if you mix one solution with another, you can get changes in volumes. Just the low interactivity of gases make this far less of a problem. Okay? And so you can treat the gases independently of one another. Now you can go a little bit further in that if you know the total pressure, even if you don't know each individual pressure, and again, this is applicable to hundreds of gases. If you know the total pressure, you can use information to tease out the pressure of each individual component without directly knowing what it is. And that uses something we call mole fraction. So we can use this idea of the total pressure being equal to the pressure of A plus the pressure of B. Well, we can substitute in our gas law in each of these cases. And if we substitute in these, we see that these share a common set of variables, and so we can do a little recombination. Pressure temperature is equal to NA plus NB, and this comes out as RT over V. If we take the individual pressure component of part A, pressure of part A, and we divide it by the pressure total, Na over RT divided by V, all divided by Na plus B, Na plus NB divided by times RTV. And due to some judicious canceling, you end up with the following. That's the pressure of A divided by the pressure of T will equal, the ratio of the pressure of A divided will equal the number of moles of A divided by number of A, number of moles of B. Well, we can define this quantity as chi. Or the mole fraction. The fraction of the moles. The number of moles of A divided by the total number of moles present. So that's mole fraction. Number of moles of the component divided by total moles. Now, mole fraction isn't just used for gases. Mole fraction also shows up around solutions and other areas in chemistry. It's very easy to generate. You count your number of moles in one component divided by the total number of moles. There's your mole fraction. If a mole fraction is 0.3, then we know that 1 out of 3 of the moles is our questionable material. So mole fraction is a nice unitless number that contains all of the mole information inherent to it. So like they like to show whenever you have mixtures. Now, what this simplifies to is that the pressure of a given component will equal the mole fraction of that component times the total pressure. Now, a simple way to say that is, in a gas mixture, the pressure of the component is proportional to the amount of material present times the total pressure. All right, so allows us to scale our pressure. What's nice is we can count the number of moles of gas, and from that fraction, we can figure out the pressure. The converse of that is also true. If we know the pressure contribution of a gas, we can calculate its mole fraction, or the number of moles present. Now, this is called Dalton's Law of partial pressures, which at its simplest basically says that the pressure total will equal pressure A plus pressure B. But the corollary of that was that the pressure of A is equal to the partial pressure of the pressure total. Sorry, the mole fraction of the pressure. The pressure of the component A is equal to the mole fraction of the pressure total. Now, where this really comes into play, is when you trap gases. Anytime, how do you capture gases? The easiest way to capture gases, if you were watching those videos, either you can take an upturned bottle, upturned container, and you can fill it with water, and you can then run a hose into it and connect that to your reaction. And out will come your gas. And slowly over time, your gas will be present. Unfortunately, above water, above any liquid, there is a small but non-negligible vapor pressure. which is basically the gas derived of the liquid that contributes to the total pressure. If you've ever boiled water, you know what happens. You boil water, the steam comes off. Well, the steam is our visible observation of water vapor that's condensing. In a hot air system, you wouldn't actually see the vapor present. But over water, there is a noticeable vapor of water. You walk into a sauna, it feels, you can feel the moisture in the air. Right? And literally, that's what you're doing. You're feeling the moisture, the water vapor present. So that means that whenever you collect a gas over water, the total pressure will equal the partial pressure of the water plus the partial pressure of the gas. And what this does is this artificially inflates the total pressure. And so we have to correct for the partial pressure of water. Lucky for us, there's this lovely little table that someone has calculated that shows the temperature dependence of the vapor pressure on water. As you increase the temperature, the vapor pressure increases. The air holds more water. Now, actually, when you get to the boiling point of water, it turns out that the boiling point is when the vapor pressure equals the atmospheric pressure. And so at that point, all of the gas above the water is steam, is water vapor. But you can use these tabulated values. So if you know what temperature you're at, 25 degrees, at 25 degrees C, 23.7 millimeters of mercury would be the contribution of water vapor to the total pressure. So right now, 25 degrees in here, assuming that there's enough water vapor, we know that the air we breathe, that out of that 760 millimeters of mercury that we're breathing, the rest, the balance, would be the gas, but 23.7 millimeters of it would be our water vapor. When we're capturing gases over water, we just need to correct for that, effectively subtracting out the contribution to the water from the total pressure. Minor correction, but non-negligible. It can alter our results. So,